Okay, so in lecture 20, we're going to start our discussion of interface thermodynamics. So we've already seen that phase separation is common in complex multi-component materials and provides a way for systems to lower their free energy, right? So this allows complex multi-component systems to lower free energy, right? But when they do, they form boundaries, right? So as a consequence, the system forms interfaces or boundaries between the phases that arise, right? And so these interfaces are actually distinct from bulk phases. So interfaces are important because they may do a number of interesting and important things, right? So they may drive segregation. That is, certain components may segregate to the boundary. They can change pressures in the system. They can alter melting temperatures. And they can also change equilibrium compositions. Or phases. So it's important, especially when the interfaces become small or we have many interfaces, to understand how these interfaces are affecting the system as a whole. And they're important for understanding the process of phase separation in general. So typically, if we think of an idealization, so ideally, an interface is a sharp delineation between two phases. And so if we wanted to draw this in 2D, of course, usually we're thinking really in terms of 3D, we would have some phase alpha that might be within some boundary, some interface here, and some other phase beta would be present outside of the phase alpha. Right? And so we're interested in looking at this interface where we cross over from alpha to beta. Right? Now it's important to realize that this is an idealization, and this idealization differs from reality in that actual interfaces are not perfectly sharp. That is, that the quantities typically vary over some length scale. So if we were to look at an interface and we were to plot as a function of position the composition, let's say, we might expect that we move from the composition associated with alpha, so let's call that C alpha, to the composition associated with beta. And in the sharp interface model, we would be at the composition in alpha, and then we would hit the interface, and we would move down to the composition in beta, and then we would have that composition. But, so this is an ideal interface. But a real interface actually might look more like this. That over some length scale, the composition crosses over, and actually it's within some width. So this would be like the width of the interface that we have a variation of material properties. Now, when thinking about interfaces, in each phase, we can uniquely define our thermodynamic quantities. So, for example, we could define the energy in the alpha phase, the entropy in the alpha phase, etc. But in the interface, since things are varying as we move through the interface, these vary with position. Okay, so now Gibbs suggested a particular way of relating the diffuse picture to the sharp picture. So Gibbs suggests a way to relate these pictures. And he would say that, okay, we can define a dividing surface. So create a dividing surface, which we'll call the Gibbs dividing surface. And you can put it anywhere, somewhere in the interface region. Where to put it is somewhat arbitrary. And then we can define excess of a thermodynamic quantity in the following way. So for example, if we wanted to define the excess energy, that would be the energy of the whole system minus the energy per unit volume in the alpha phase times the volume in the alpha phase, given where we've put our sharp interface, minus the energy per unit volume in the beta phase times the volume of the beta phase. Right? And we could do this for any quantity. So we could have an excess entropy. That would be the total entropy minus the entropy per unit volume in the alpha phase, volume of the alpha phase, minus the entropy per unit volume in the beta phase, volume of the beta phase. We could do that for any thermodynamic quantity of interest. Now, in general, these depend on where you put the dividing surface, but you can show that there's one combination of excess quantities that actually is invariant of where you put the dividing surface. So one quantity invariant of location of dividing surface, and that would be the excess energy minus T times the excess entropy plus P times the excess volume minus the sum over all components of the excess number times the chemical potential of each divided by the area. So this is an invariant quantity, doesn't depend on where we put our dividing surface, and that is going to be how we define the surface energy, which we'll call gamma. Okay.